Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll begin a new unit called 3D Geometry. So we've learned a lot of different things in two-dimensional coordinates, such as the distance formula, the angle between two vectors, and so on. And now we are going to extend that to the natural three dimensions. So let's just take a small brief recap of the stuff we learned in vectors because that will be important. So the x-axis and the y-axis were two mutually perpendicular axes. Once you decide the x and y-axis, you have two options for the z-axis. They will obviously be perpendicular to both the x and y-axis, which means they'll be perpendicular to the plane of the screen on which you're watching this video. But they can be towards the viewer, towards you, or away from you, which means the positive z direction can be this direction, towards the viewer, or away from the viewer. So, which one of the two is it? Well, the convention is we choose what is called the right-handed coordinate system. And throughout pretty much all of maths and physics, you'll be using the right-handed coordinate system, in which if this is the x direction, this is the y direction, then there is a way to figure out the direction of the z-axis. You put your fingers of your right hand along the x-axis and you curl them such that they move towards the y-axis. Then the direction of your thumb will be the direction of the positive z-axis. So if you were to take your right hand and put it along the x-axis, put your fingers along the x-axis and curl them towards the y-axis, your thumb will point towards you. Right? It will be opposite for the left hand, so make sure you use the right hand. So if this is the x-axis, this is the y-axis, then the z-axis by convention is taken to be this, which will point towards the viewer. So this will basically be the z-axis coming out of the plane going towards the viewer. This is another way of saying something which we already know, which is I cap cross j cap is equal to k cap. So we'll just take a brief recap of what these are. The unit vector along the x direction, that is a vector which has a direction along the x-axis but has a magnitude of 1 unit, is called the I hat vector. So I hat is the vector, or rather the unit vector along the x-axis. Similarly, j hat is the unit vector along the y-axis. And we've studied in the previous unit how to add two vectors, subtract two vectors, multiply a vector by a scalar. But there are some other things also we studied, how to take the dot product and cross product of two vectors. And in that we learned that I cross j could either be defined to be k or minus k, and every other one would follow. So this is basically a convention, and this arbitrary choice, k instead of minus k, is basically the same as saying z will point towards the viewer, not away from the viewer, if this is x and this is y. Right. And the unit vector correspondingly in the z direction is called k hat. Now this right-handed coordinate system goes every which way. So for example, let's say this was the x-axis and this was the y-axis. The x-axis was towards the viewer and the y-axis was towards the right. What would the z-axis be? Will it be, it will obviously be perpendicular to both of them, but will it be in the upward direction or the downward direction? Well, once again you can use the right hand rule. If you point your fingers to yourself and curl them towards the right, it will take a couple of times to get the hang of this. You'll see that the z-axis has to point upwards. So once again, you can choose any two directions to be the x and y axis. Once you decide that, the z-axis is decided by this. Now, just like in two-dimensional geometry, every point on the xy plane could be represented by two coordinates x, y. Now we'll need three coordinates because it has to have a z component as well. So every point can be represented in three-dimensional geometry by a set of three coordinates x, y, z. Now again, similar to the two-dimensional case, the vector joining this point to the origin, let's say this is O and this is P. So OP, the vector, is called the position vector of the point P. The vector joining that to the origin. And how will we write it? It can easily be written as x I cap plus y j cap plus z k cap, because the x component will be the x coordinate, the y component will be equal to the y coordinate, and so on. If you have another point, let's say this is x1, y1 and z1. Say you have another point q which has the coordinates x2, y2 and z2. Then the position vector of q will be OQ. That will be x2 I cap plus y2 j cap plus z2 k cap, where this is 1. And then what you can do is you can subtract the two vectors to get this vector, which is the vector PQ. You can calculate the distance between the 2 points. For 2 dimensions, it would be root of x1 minus x2 whole squared plus y1 minus y2 whole squared. For 3 dimensions, we would add one more thing, z1 minus z2 whole squared. So let me just show you a simple proof of that. It comes from a simple generalization. So first let's look at the 2-dimensional case. Say x1 comma y1, and this is x2 comma y2. Then you can use the Pythagoras theorem after this construction. This total distance would be x2 and this distance would be x1. So this distance would be x2 minus x1. Similarly, this distance would be y2 minus y1. And so by Pythagoras theorem, the length of this side, which would be the distance, would be root of perpendicular square plus base square. So x1 minus x2 whole squared plus y1 minus y2 whole squared. Let's generalize this to 3 dimensions. So this is x, this is y, this is z. Let's take one point x1 comma y1 comma z1, and let's take another point somewhere else. Let's say here x2 comma y2 comma z2. Right. So they'll have their intercepts on the xz plane. So this point would be z2. Similarly, this point would be z1. This would be x2. This would be x1, and similarly for y. This would be y2. This would be y1. So we need to find this distance between these two. So that will be, we can use the Pythagoras theorem for this side, these 3 sides. We can do it any combination. I'll do this combination because y is the vertical one which I've chosen. Again, x cross y is equal to z. That always has to be true. So this side is, this is y1, sorry, y2 minus y1. And now we need to find this side. So this side is basically this side, the projection of this side, right? And what is this side? Here you have x1 minus x2 minus x1, and here you have z2 minus z1. So from the Pythagoras theorem, if this side is d, what we get is, this is d, so this is d, the hypotenuse. D squared is equal to x1 minus x2 whole squared plus z1 minus z2 whole squared. Now once you have the square, it doesn't really matter whether it's x1 minus x2 or x2 minus x1. And obviously, so this is d, the root of this, and this is y2 minus y1. So this side is given to me to be root of x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square. Right, so basically 2 applications of the Pythagoras theorem, one in the xz plane and the other with that line and the y direction. Similarly, there are a couple of other generalizations which we'll quickly see. When you have a1 I cap plus b1 j cap plus c1 k cap and a2 I cap plus b2 j cap plus c2 k cap. Let's say this is a vector p and this is a vector q. Then p dot q, we saw this for 2 dimensions in vectors, is simply a1 a2 plus b1 b2 plus c1 c2. And similarly, you can get p cross q, and you'll have to multiply, and there'll be 9 terms. So I'll just do it quickly to show you. It's exactly the same as when you do for 2 dimensions. What you have to remember is I cross j cross k, and this is the direction for the arrow. So you go in the direction of arrow, it's a plus, otherwise it's a minus, meaning I cross j is k, j cross k is I, k cross I is j. If If you go in the other direction, I cross k is minus j, k cross j is minus I, and j cross I is minus k. So this cross this gives me 9 terms. Let's take the first term with these. I cross I is 0. I cross j is k. So I get a1, b2, k. Then I cross k is minus j. So minus a1, c2, j. Then you have multiplied this by the 3 terms. So j cross I is minus k. So you have minus a2, b1, k. J cross j would be 0, j cross k would be I, so plus b1 c2 I, and then you take this, so k cross I would be j, so plus a2 c1 j, k cross j would be minus I, so minus c1 b2 I. Now you don't need to remember this formula, there is actually a way to remember this, but I would suggest you just multiply this, and the more you do this, the quicker you will be able to do this with enough practice. So we see that the generalization from 2 dimensions to 3 dimensions in most cases is quite natural and intuitive. In the next video, we'll start looking at actual generalizations of some important concepts from 2 dimensions, and they'll actually be important enough that we'll study them in quite detail. The next video will focus on the generalization of straight lines to 3 dimensions. So for example, you can have a line in 2 dimensions, 2x is equal to 3y plus 9. What does a similar line look in 3 dimensions? So that's what we'll study in the next video. Thank you.